Urban water delivery relies on a continuous balance of pressure and volume. Municipal systems are engineered to maintain a specific baseline of hydraulic pressure, pushing water from central treatment facilities through a network of subterranean pipes to residential endpoints. Under standard operational conditions, daily demand remains within projected parameters, and the flow remains constant. The architecture is designed for average consumption, not peak emergency drain. During localized emergencies or periods of acute environmental stress, the immediate response of both residents and emergency services is to increase draw. Homeowners connect garden hoses to dampen structures. Firefighters connect high-volume pumps to municipal hydrants. The underlying assumption guiding these actions is that the available supply will scale proportionally to meet the sudden necessity, simply by opening the valve wider. However, centralized distribution networks possess a fixed volumetric capacity. When multiple endpoints draw simultaneously from the same main line, the system experiences a phenomenon known as hydraulic collapse. The physical volume of water moving through the pipes cannot outpace the aggregate demand at the periphery. As the number of open valves increases, the pressure drops across the entire grid. In high-demand scenarios, such as a wildfire affecting a localized area, hydrants lose pressure and residential taps run dry. The infrastructure does not lack water at the source. It lacks the physical capacity to deliver sufficient volume under simultaneous, concentrated demand. The system's architecture creates a hard ceiling on output at the exact moment output is most required. Because centralized grids are structurally bound by these pressure dynamics and mainline capacities, alternative formats for water acquisition exist. Decentralized point-of-use generation bypasses the distribution network entirely, removing the dependency on mainline pressure and central volume. By sourcing water independently of the subterranean grid, these formats operate outside the physical constraints of simultaneous draw. One such structural response is the smart water box. It functions as an atmospheric water generator, extracting moisture directly from the ambient air rather than drawing from the municipal supply. Because it operates as an independent, localized node, its output is not subject to the hydraulic limitations or pressure drops of the central grid during high-demand events. Centralized water infrastructure provides reliable delivery under baseline conditions, but its architecture dictates a strict mechanical limit on volume during crisis events. Understanding the physics of pressure dynamics reveals the operational boundaries of grid dependency. For those assessing these structural constraints, alternatives that generate water outside the centralized distribution network present a distinct operational paradigm.